All right, page 205 in your textbooks. We looked yesterday at several example problems and kind of worked together on torque problems where there's multiple torques, multiple forces acting on a body. And of course, we said all the forces have to cancel to achieve class translational equilibrium. And then all the torques have to cancel to produce rotational equilibrium. And so we're looking for both things to cancel. Go and read problem 20, and a very, very interesting problem. Kendall, seem like the kind of person who might go on a safari sometime, so here we go.
Two safari guides are carrying a pole from which hangs a dead lion upside down. The lion weighs 1,300 newtons and its 4 feet are tied 1.3 meters from the front of the pole and 1.4 meters ahead of his hind feet. His weight is equally divided between the 2 points of suspension. The pole, weighing 120 newtons, is 5 meters long. If the carrier in front holds onto the end of the pole, where must the carrier in the back hold the pole if he wishes to bear half of the weight?
All right, so dead lion. Here we go. Hopefully not an endangered species. So here's the pole. It is 5 meters long. That's longer than this chalkboard. It's a very long pole. All right, 5 meters long. And at the front end of the pole, holding the very end, is guide number 1. Somewhere in the back, presumably not at the end, is guide number 2. We all catch these, not necessarily at the end. He's somewhere back here. We're not really sure where. That's kind of the question, is where must he be? And those are the 2 forces that hold the pole up. Now there are also 2 forces pulling down. And the 2 forces pulling down, class, are the weight of the pole itself and the dead lion. Okay, so the pole, of course, is going to be exactly halfway in between, and then right in the very middle. But the lion, they go through great lengths to describe the placement of the lion. All right? And you wonder, why didn't they just put him in the middle of the pole? They didn't think about it when they first strapped his feet to the pole, that we should put him in the middle. So it says that the lion's 4 feet are 1.3 meters back. Now remember, the whole pole is 5 meters, so the halfway point is at 2.5. So we're coming back 1.3. That's a little over half of this distance. So right about here is where the 4 feet are tied. Those are his 4 feet. His hind feet, it says, are stretched out, so they are
1.4 meters.
That's actually not that stretched, actually. They're because I figure a lion's probably usually longer than 4 feet long. So anyway, 1.4 meters back, which again, if you go 1.3, an additional 1.4 would be what total distance from that front end? 2.7. This is at 2.5. So the 4 feet are right about, the hind feet are right about here. But the weight doesn't pull down at the hind feet or the 4 feet. The weight pulls down in between. So right in between these is where the lion's force bears down. Now, if they're 1.4 meters away, the halfway point is going to be how much further behind the 4 feet? 0.7 meters, which since the 4 feet were 1.3 meters from the front of the pole, the weight of the lion is how far from the front of the pole? 2 meters even. Couldn't just come out and say that, no, because you're seniors. They wanted to make you think about it. How many figured out that the lion's weight is basically pulling 2 meters behind the front end of the pole? Only Audrey. Questions? All right. Does it make sense now? How to think that through? Again, there were a lot of numbers given. By the way, everything seems to refer to from the front of the pole, the front of the pole, the front of the pole. That gives me an idea. Maybe I should pick the front of the pole to be my pivot point. That's the pivot. So that the lion's torque of, how much did the lion weigh? 1,300 newtons. The lion's force of 1,300 newtons applies a torque at a radius of, we said, 2 meters. The pole, which only had a force of 120 newtons, it has a radius of 2.5 meters. And then there's the guide in the back, and his radius is, that's the whole point. We're trying to figure it out. So we'll call his radius x, because we don't know it. Now, the radius here, of course, is 0. So regardless of what force is applied, it really doesn't matter too much because the torque disappears. But we do know this, that total, how many newtons of weight bear down? 1,420 newtons down. Again, we have to balance that translational equilibrium. That means there's got to be 1,420 newtons up. And it said that the guides are supposed to carry half the weight each. Each is supposed to carry an equal amount. So the guide in the front, even though we don't care, ends up carrying how much weight? 7 or 10. We don't really care. The guy in the back ends up carrying how much weight? 710 newtons. We do care about him. So we have this torque, and this torque. And the beauty, again, of putting the pivot at the end is if they're down, they all work together. Even if there were another force at the other end pulling down, they would all be working together. Which direction? Counterclockwise. These are both counterclockwise. Though, again, if you mess that up, it doesn't really matter that much as long as the pivot's at one end. As long as you realize the downs are all going to work together, and of course the up will be the other direction. Up happens to be clockwise about that pivot point. So what's the equation we should have used, Michael?
The sum of all the counterclockwise equals the sum of all the clockwise.
Okay, so what would be the sum of all the clockwises?
710.
That's the force. We need a torque. Force times radius, so 710x. That's the sum of all the clockwises. All right, now we need all the counterclockwise and what would that sum end up being here, Michael?
1,420 newtons. Wait, no.
Remember, we're going to take this torque plus this torque. It's not a problem, by the way, if you just write out force times radius plus force times radius that way. You could do that, or you could do 2.5 times 120 in your head class, or on the calculator. 300 plus 1,300 times 2, we can do that in our head for sure. 2,600. In fact, we could add those together to get 2,900, and then to solve for x, we just have to divide away the 710, and so we divide 2,900 by 710, and what do we get for the x? 4.084, blah, blah, blah. How many sig figs are we allowed in the problem? 2, consistently 2, so, though it doesn't really matter if it's consistent or not if there's 2. Anyway, and we get
4.1 meters.
4.1 meters, but we can't just say x is 4.1 meters, because it said, where should he hold the pole? Ooh, I know, he should hold it at 4.1 meters. Huh? 4.1 meters from what, class? From the front of the pole. Now, let's think about it. Is that a good logical way for him to do this? Got the line laying there in the middle. He's dead, so it's okay. And we go all the way to the front. Let me measure back 4.1 meters. Probably not. What would be a much more practical way if he felt he had to measure this? What would be a more practical way?
28.
Measure up from the back end, right? So if I wanted to change the number to be a little bit more logical, we don't have to. I would take that answer on a quiz or test. But a more logical answer would be to subtract that from the 5. And if we did, we would get 0.915 around 0.92 meters from the back end. And that's a better way to write the answer, though I wouldn't take points off for the other, but I like that one better. It just makes more sense. That's the most logical way is, hey, slide up 91.5 centimeters from your end. Come up about a meter, a little less than a meter up, hold it there. Make sense? Questions on the problem? Audrey, did you get one of those answers?
No, I got close.
Got close. Did you get the equation, or was that where things kind of went wonky?
Yeah,
As
I
Michael
didn't
might say.
get the equation. I actually split the lion's weight in half because I don't know why.
Gotcha. Okay, so that kind of threw things off then. All right. Questions from you two? And you're good now? All right. Let's flip back, if you would, to page 203 then. Let's take a look at another one. Now, all the torque problems we've worked so far have always dealt with where, right? We've always been finding a distance or a radius, if you will. Let's look at an example where we know all the distance is. It's an actual force that we're curious about. And read the example problem for us, if you would, Michael.
13.4.
Example 13.4, there on page 203.
A uniform table weighing 119 newtons is 2.66 meters long. A 114 newton bag of sugar sits on the table directly over the legs on the left side of the table. A boy weighing 396 newtons stands on the table 0.45 meters from the right end. Find the upward force of the legs at each end of the table.
Boy should not be standing on table, should he? Right? How many, that was your first thought as he was reading? It's like, no, he should not be up there. All right. But for the sake of physics, we'll just work the problem. So they've given you the free body diagram already, right? We've got this table, and the table weighs 192 newtons. Now it says it's a uniform table. That means assume uniform distribution of mass. It may not actually be. Think about it. Think about how the underside of a table has that metal framework. There's more metal framework at the ends, isn't there? So technically the mass wouldn't be evenly distributed, but for the sake of the problem, even distribution of mass means the weight is basically in the center, right? So if it weighs 192 newtons, we'll put the table's weight right in the middle. And then it says we've got a 114 Newton bag of sugar directly over the legs on the left side. So we go to the left side, and there's a bag of sugar sitting on top of the table. That's also weight bearing down. And the bag of sugar weighs, that's a big bag of sugar.
114.
114 newtons. Goodness, that's, 20, almost 30, coming up on a 30-pound bag of sugar, between 25 and 30 pounds. That's a big old bag. And it's a very lightweight table. Well, no, I won't say very lightweight table. It's a 40-pound table. 40, 50 pounds. It's a decent weight. Okay. And then we got a boy who's Kendall size. Okay, so he's not breaking the table, okay? But still, boy is standing on the table, and he says he comes in from the right end, 0.450 meters, and there's boy. Another 396 newtons bearing down. I think that's all the things that bear down. Yes. All right. There is, however, something that's pushing up on the table to counter all of this weight. What is countering all of this weight, class? The legs of the table, right? And let's assume the legs are at the actual end. Again, I know folding tables, the legs are usually inset about 6 to 12 inches. But we'll just say the legs are at the end. I don't know if it says that in the problem, but we're going to have to kind of assume that here. We have to assume the placement anyway. We might as well put them at the ends. And the problem is, I don't know that the legs bear half. In fact, I'm confident the legs do not each bear half the weight. Does that make sense? The weight is all shifted this direction. So these legs are going to actually support more of the weight than those legs because this side of the table is weighted more. Does that make sense? So the question is, what is the force right here? Well, I don't know. What's the force right here? I don't know. So one of the forces, class, is going to get to be X. How would I represent the other force? Total weight minus X. The total weight that is being supported minus however much of that weight is supported by the one side. Now, here's the key. I've got to pick a pivot point, right? Where would be the ideal pivot point? And you say, but Mr. Nadesky, they already referenced a distance from that end. I know, but if I put the pivot here, both torques disappear. Less to deal with, less math. So I'm going to call this here my pivot point, in which case I do not want to call this force X, and that the big binomial total minus X. I want to call this one X, and I don't even care what total minus X is, because it cancels out anyway. Does that make sense? So there are ways you can outsmart the system a little bit. I don't know what the weight is, but it doesn't matter because its radius is 0. So in both cases, these torques are all gone. So far, so good? Now, it does tell me that the table's total length. You notice the length always has to be known, right? The lengths of these objects we're dealing with have to be accounted for. What is the length of the table? 2.66 meters. That's about an 8-foot long table, like the 8-foot tables we have at the in the lunchroom. And so, if this is the pivot, and the table's 2.66 meters, what is the radius of the right side legs? 2.66 meters. What's the radius of the table's force? Half of it, 1.33. And now account for this, 2.66, but we came in 0.450. What's the radius of the boy standing on the table? 2.21 meters. Questions on the setup? Do you see how it's really not that different than finding a radius when we find a force? Now, again, there were 2 forces I didn't know. But by putting the pivot point at one of the 2 unknown forces, I was able to kind of get off the hook and just call the single unknown force I care about X. Do we understand the way I set this up? All right, so now we solve. If this is the pivot, both down forces, class, are producing what direction of torque? Clockwise rotation. So these two are my clockwises, which means this guy, the only up torque, which pushes it then counterclockwise. All right, at your seats, write the equation. Kendall, tell me what equation you're writing.
The sum of the forces.
So tell me what to write. Like,
The 192 x.
it's not 192x.
No, 192 times 1.3 equals.
What direction was this torque again?
Clockwise.
It was clockwise. So was this one. Then since they're both clockwise, we just need to make sure we keep them together. So I'll take the table's torque clockwise plus
2.21 times 396
there we go. And then those two together are going to
equal 2.66x.
there we go. And of course we'll simplify some of these numbers here. Let's see, what is 192 times 1.33? 255.36, and then 2.21 times 396 is
875.16.
all right, and of course combine that together and we get
1,130.52.
and that's all equal to 2.66x, so just divide away the
2.66.
and how much force is being held up by the right side table legs?
425.00.
Almost exactly 425 newtons. But notice what the question asks. The question says, find the upward force of the legs at each end of the table. Well, I found the right side legs to be 425 newtons. How would I come back then and get the left side legs?
Minus x.
What is it?
Total minus x.
Total minus x. So in order to solve that, then I need to know the total. I need to take the total weight downward, and I think I might have been wrong on my initial projection. I feel like the right side, yeah, that's true, because the weight over here is so small. There's the bigger weight is on this half at least, even though it looks like the weight's shifted. So I think the right legs are actually going to carry more. Anyway, so we figure the total weight, and what is the total weight, class? 702 newtons. 425 of them are being supported by the right legs, so the left legs are supporting 277 newtons. 277 newtons. So even though the forces were shifted this direction, the significantly greater force was on that side, hence right side legs actually carried more of the weight. So I was wrong in my initial guess. Questions on this? Now again, what if we had picked this end to be the pivot? Okay, then I would have called this force x, and that would have been my total minus x, so I wouldn't have had to mess with it. Radius would have been 0.45, radius still would have been 1.33. X and 114 would have both had radii of 2.66. I would have had 3 downward counterclockwise forces working together and 1 clockwise force opposing them. Still would have gotten the same answer, except my x would have been the 277, and then it would have come over here to get the 425. And we've already established we don't want the pivot anywhere but an end. Okay, questions on the example? All right, let's look at a similar problem then. Page 205. Page 205, and I say similar, I don't know how similar this is actually. Number 18. Go ahead and read number 18 for us, Audrey.
A meter stick balances on a knife edge at the 50 centimeter mark. When 2 nickels are stacked over the 12 centimeter mark, the loaded stick is found to balance at the 45 centimeter mark. Nickel has a mass of 5 grams. What is the mass of the meter stick?
Now, when they say knife edge, it's not a real knife. You remember the balance we used to do the lever lab a while back when we did the machines lab? The lever that pivoted, that balance it was on is called a knife edge balance. So it's not a real knife. So no one's hurt in making this problem, lest people be offended. And it's a meter stick. Remember I said you always need to know the length, right? Thoughts, class? It's a meter stick. So what's the length? 1 meter, very good. All right, now the only thought is everything else throughout the problem isn't given in meters. Everything else is given in centimeters. Now here's the thought. Normally we have to convert everything to meters, right? But if every single thing is centimeters, what's going to happen to all the centimeters in the problem? They're all going to cancel anyway. So I'm actually going to go with, to avoid decimals, I'm going to say that the length of the meter stick is 100 centimeters. And I feel like that might be a better way to approach it, just trusting that all the centimeters will balance out. Unless I'm finding a radius, in which case I'll just make sure I put it in centimeters. All right, so let's see here. We say it balances right at the 50 centimeter mark. So right at the very middle of the meter stick, that's where it's being balanced. So that's the one force that holds it up. Do we see that? Well, not only does it hold it up, but right at the very middle class, bearing down, assuming it's of uniform density throughout, we also have the force that the meter stick bears down. So the meter stick bears down, this pushes up, and that's why theoretically, if you balanced the meter stick perfectly at the 50 centimeter mark, it should balance level. Now, you might remember my meter stick didn't actually balance perfectly level. So mine was not perfectly uniform mass, but we're going to assume that here. Then it says we got 2 nickels stacked at the 12 centimeter mark. So come in here, 12 centimeters, we have 2 nickels. Well, what good does that do for me? Well, it tells me later on something about a nickel.
It has a mass of 5 grams.
It has a mass of 5 grams. So if there's 2 nickels, that's a mass of 10 grams. Well, again, we don't really want mass. Generally, we want weight, correct? But if I take mass and I multiply by gravity every time, you realize gravity could cancel away also? For that matter, this is in grams. I normally want, but as long as it's grams everywhere, that'll stay consistent as well. So there's some shortcuts we can take to cheat the system. Now, I told you it balanced at the 50 centimeter mark. But then all of a sudden they say we put these 2 nickels here, and suddenly it ain't balancing at the 50 centimeter mark anymore, is it? I didn't read far enough. Now it balances at the
45.
Now the mass of the meter stick, or the weight of the meter stick, will still bear down at the 50 centimeter mark. And by the way, the reason they said it balances was they're basically saying it is of uniform mass. That was their way of saying it was of uniform mass. I just hadn't read the problem far enough to realize that. Okay, so they were saying unweighted, it balances perfectly, it is of uniform mass. So we have this upward force of the knife edge balance, the mass of the meter stick bearing down, and then we have the what you call mass of these 2 nickels sitting there at the 12 centimeter mark. Is there anything else in the problem? That's it, right? So we have 45.5 centimeters to this particular force, whatever it is, and then we have another 50 centimeters here to this point. So those are the 3 forces acting on the meter stick. The question is, I know all 3 radii, right? What I don't know is how much this particular Dumaflanger thingy is, right? I don't know its mass. So we'll call the mass x. So I have a mass and a distance. I have a mass and a distance. Is it possible to come up with a supporting mass? No. Though you could say the force will be equal to the combined mass times gravity, and if we're already going to divide out gravity anyway, you could say the force here, or the mass supporting, is x plus 10 grams. Make sense? Now here's the question, where do we want to put the pivot? Normally I say put the pivot at one end, and I could do that, but none of these torques would cancel out. And maybe that's fine. I just say these 2 downs equal the up and we solve. Or if I put the pivot here, I wouldn't have to worry about the binomial anymore. I would just recognize that these are opposing each other at that point. So here's the question. How many say, I like the consistency of putting it at the end. I don't care that nothing cancels. Let's put it at the end. I didn't think so. How many say, let's put it where the real pivot is so we can get rid of the binomial and not have to worry about it? Or the crazy decimal. We like that. Everyone's in agreement on that. This is my pivot. Therefore, this radius is now 0. Now be careful. We came in 45.5 to the pivot. It's 50 to where the mass is concentrated for the meter stick, the center of mass. What is actually the radius now then? Just 4.5 centimeters. And we said it's 45.5 to the pivot. We come in 12 to the 10 grams. Oh, we're not dodging decimals, are we? No, rats. What is the actual radius to where the 2 nickels, the 10 grams, are stacked? 33.5 is actually the radius. This one will act in which direction, class?
Counterclockwise.
Counterclockwise. This one's going to act in which direction?
Clockwise.
And they're the only 2 ones left, right? They're the only 2, so the one equals the other. So we can say that 10 times the 33.5 equals x times the 4.5. Again, had we multiplied gravity, gravity would cancel from both sides right now. Had we changed to kilograms, the shift would cancel itself away. Had we changed to meters, that would have all shifted away as well. That's why we're able to cheat, okay? We can't cheat normally, but this time we can cheat. And what do we get for the mass of the meter stick? Class?
74.4.
74.4 repeating. How many sig figs? Everybody's got 3, so 74.4. We're looking for a mass.
Grams.
Normally kilograms, but here it's grams. It's a 74.4 gram meter stick. There's no way you could have found that with just forces, but as soon as you incorporate the idea of no rotation, rotational equilibrium allows us to solve it. Now, because I'm evil, we're going to do it again, and this time we will put the pivot at one end. Well, now all of a sudden, because it's at one end, the 2 downs work together. 10 grams had what radius if we put the pivot at this end? 12. So 10 times 12 plus, we don't know this force, so we call it, but we know its radius. 50. And then we said this one has a force, if you will, of a mass supporting of x plus 10, because it's supporting both the x and the 10, and has a radius of 45.5. At your seats, solve. Do you get the same answer? Should have gotten the 74.4 grams again. So either one would have worked. Do we like the process we went through of calculating the 33.5, the 4.5, and do we like this better, or feel like maybe that was easier? Or do you feel like they're about the same? First easier, second easier, or same? First easier? So we made the right decision then. There we go. Again, just showing that it could work either way. Number 19, kind of a similar problem. Number 19, read that for us. I think we're to Kendall again.
A 10 Newton meter stick rests on a pivot at 25 centimeters and a boy holds the other end, exerting a force in the vertical direction. The stick is loaded with 75 newtons at 5 centimeters, 27.5 newtons at 75 centimeters, and 12.5 newtons at 90 centimeters. How much force does the boy exert on the stick, and how much force does the pivot exert on the stick?
Notice this time the forces are given in newtons, not masses in grams. Great, then we'll just roll with newtons, right? We can roll with whatever units. Notice the distances are still centimeters, and it's still a meter stick. So once again, we're going to start off with our 100 centimeters. Again, always account for the length. Now, right off the bat, it tells us that this meter stick has a mass of 10 newtons, and that's going to be smack dab in the middle, 10 newtons. But it rests on a pivot that is at the, so exactly halfway between those is where the pivot is. Is that thing going to balance? No. What if we load it up with a bunch of weights? Maybe if you place them just right, but it doesn't sound like we place them just right to balance, because it says that at the other end, a boy has to exert a force. A boy has to hold it up. So here's the boy down here, and here's the pivot here. Now we may not actually call this our pivot point, but that's where the actual physical pivot is. We can name our pivot point wherever we want. So pivot and boy are what's holding up this meter stick. There's more weight than just the meter stick, of course. It says at the 5 centimeter mark, class, we loaded up with 75 newtons. Then at the 75 centimeter mark, we loaded up with
27.5 newtons.
And then at the 90 centimeter mark, we load it with
12.5 newtons.
And the question is, what point do we want to be the pivot? Because that's going to determine the radii we choose, right? I'm not going to write all the numbers they gave for the locations if they're not going to end up being the radii anyway. Again, if you want to do little math, go ahead and call this first end the pivot, so at least literally the numbers they gave you are the radii. Does that make sense? The downside, of course, is nobody cancels. However, it wouldn't be hard math if we made the boy's end the pivot. For one thing, I don't have to worry about his force. The boy just drops out, right? And all I have to do is kind of think reverse of all the numbers they gave. So if the whole thing's 100 centimeters, and this is at 90 centimeters, class, what is the radius? 10 centimeters. This was at 75, that is the radius from the other end is
15.
Ooh, 75 from 100? 25 centimeters. Of course, the pivot, the meter stick is still going to be in the middle, which is going to be at 50 centimeters. The pivot was at the 25 centimeter mark, which means from the far end that comes in 75 centimeters. And then this was at the 5 centimeter mark, meaning its radius is 95 centimeters. Notice all of these, because we put the pivot at an end, are all working downward counterclockwise. This is the only one countering all of them now going clockwise. I just don't know the force, so call it X. Technically, what would be the boy's force? Total minus the X, right? But I don't feel like doing the total, so I'm not going to mess with it right now. I'm going to have to come back to it because they ask for the, well, let's go ahead and do it. Let's find the total. Because we have to find the total eventually anyway. So 10, 27.5. Now what's the total force? 125. So the total force of weight is 125 newtons. The boy is supporting 125 minus X, but again, I don't have to mess with the binomial because I canceled the boy out. Keep going. His radius is 0. Add your seats, write the equation. technically, of course, you could use parentheses and plug it all in at once on your calculator. The only reason I show it partly is for your benefit. If I were doing it just for me, I might go ahead and use the parentheses. I do like seeing that I'm taking care of everything and I don't accidentally miss something. There's 4 down arrows. There should be 4 torques in Newton centimeters, not Newton meters, but 4 torques. I've got all 4 of them. 75 times 95, 10 times 50, 27.5 times 25, 12.5 times 10. On the other side, of course, is the only clockwise 75x. Add them up, divide by 75. Do we get 112.5 newtons upward by the pivot, the physical pivot? Which means the buoy, I mean, it almost balanced, actually. The buoy only had to provide 12.5 newtons upward, right? So not a whole lot of force needed by the buoy there. Questions on this? Do we feel like we've got the idea of how to place the torques or the forces, figure the torques with their radii, get the answers? Your turn then to do number 17. At your seats, number 17. I'll give you about a 3-minute head start and then I'll get working on it also. We are going to go much faster than well today. Sorry. He moved. Oh, he's sitting next to the computer. Like an old man. Did we get the 3 downward forces correct and we placed our legs, at the ends of the bench? What's the best pivot point? The left end. Because now we cancel out the lady and we cancel out the left legs. If we make this the pivot and it said the man was 0.72 meters to the lady's right, what's the man's radius? 0.72. If it's a 1 meter long bench, what's the radius of the bench's force? 1 meter. And what's the radius of the left legs? 2 meters. How to represent the force that the right legs exert? Because I don't know. And so what's the equation going to be here? Let's take the easy part first. Let's take the right legs. The counterclockwise torque. 2x is going to equal, let's take the bench, that's easy. 354 newton meters plus the not as easy part, but we have a calculator, so it's not bad either. The man. On the right side, How much do those legs support? I got 423.6.
Yeah.
Oh, I didn't divide it. Yeah.
Oh, okay. So 423.6 approximately, is it 2 sig figs or 3 here? It is 3, so we'll say approximately 424 newtons support on the left side. How would I figure the left side? Total minus x. So at your seats, figure the total, subtract away the 423.6. What is the total weight? That's the left leg, that's the answer there, but what was the total weight we had to find first? It should have been a total of 1,377 newtons. And the reason I point this out is because it'd be easy to say, oh, we just need to add these two because this cancel. No, it's torque cancel. The force and weight is still there, right? So we can't say, oh, we don't have to worry about that weight. Yes, we do in total weight. It's just rotation it cancels. Translation we have to account for. So when you add these all together, 1377 newtons, only 423.6 are supported by the right legs. How much by the left legs, class? 0.4 or rounded off, it will be 953 newtons. Do we feel like we understand both types of multi-torque problems? The kind where you're finding forces or the kind where you're finding a location, a radius? Do we feel like we can work it both ways? Any questions at all? All right, well, as I stated before, Monday in our next lesson, lesson 102, is going to be our review lesson. Tuesday, lesson 103 will be the test. Most of this is math. I mean, there are some terms. There's not a lot. Most of this is math. So I have a handout for you. And of course, if you're watching on YouTube, it's in the description of the video. 7 math problems for you to work over the weekend. We'll go over these in our next lesson. We'll review what few terms we have. Equations are big to know, right? Because there's a lot of math and not a lot of terms, you got to know your equations. Got to know what symbols represent what, right? There's not a lot of definitions. There's a lot of keeping track of what symbol is what, and then a lot of math. So it's going to be a little bit of a different type of physics test for you. Again, homework is do the handout. We'll go over the handout and do a review on Monday. Tuesday test. Have a wonderful weekend. And when the bell rings, you'll be dismissed.